Hi everyone and welcome back to Data Science with Marco. Today we're covering support vector machines, or SVM, yet another algorithm for classification. As always, we cover some theory at the beginning and then we move on to some coding. And in this time, we're going to go through 4 different examples. Let's get started. Let's start with some theory about support vector machine. For classification, we have seen quite a few algorithms such as logistic regression, LDA, QDA, and decision trees. Support vector machine is another algorithm used for classification. Its main advantage is that it can accommodate non-linear boundaries between classes. To understand SVM, we must first understand the maximal margin classifier. Like I said, the maximal margin classifier is the basic algorithm from which SVM extends. It relies on separating different classes using a hyperplane. In a p-dimensional space, a hyperplane is defined as a flat, affine subspace of dimension p-1. Therefore, in a 2D space, the hyperplane would be a line, and in a 3D space, the hyperplane would be a flat plane. The equation for a hyperplane is defined like this, where p is the number of dimensions. Here is an example of a hyperplane in 2D, which is represented by the line. If an observation satisfies the equation we just saw, then the point is on the line. Otherwise, it is above or below the hyperplane. Now realize that if data can be separated perfectly, then there is an infinite number of hyperplanes, but we only just want one. So that's why we use the maximal margin hyperplane, or optimal separating hyperplane. To find it, we calculate the perpendicular distance between each training point and the hyperplane. That distance is called the margin. Then, the optimal separating hyperplane will be the one with the largest margin. Here, you see an example of a maximal margin hyperplane, and you see the margin illustrated by the arrows. Notice that the plane depends only on the closest points, known as support vectors. And if those points move, then the hyperplane will move. But what if there is no clear separation between the classes, as shown here? That's when SVM is required. As I mentioned, SVM is simply an extension of the maximal margin classifier. This time it uses kernels to enlarge the feature space to accommodate for non-linear boundaries between classes. A kernel is simply a function that quantifies the similarity of two observations. The kernel can be a function of any degree, but of course, if the degree is greater than 1, then we add more flexibility to the boundary. Here is an example that we will implement later on during the coding portion of this tutorial. Here, the classes can be linearly separated, so it is easy enough. However, notice the outlier on the left. We can use regularization to account for it or not, and that will impact how well our model generalizes later on. Here is another example that we will code. As you can see, the boundary is definitely not linear, but SVM does a great job at finding a boundary and separating each class. So that's it for the theory. Now let's apply this algorithm in 4 different scenarios. Alright, so prepare your notebooks and grab the data from the link in the description. In this tutorial, we're actually going to import 5 different data sets. So you can see I'm checking them right now. So x6 data 1, 2, 3. And then spam test and spam train.mat. So as always, we start off by importing all the libraries that we will need throughout this project. By the way, these exercises are taken from the machine learning course by Andrew Ng. I am simply solving them using Python here. By the way, it's an amazing course and I will leave the link in the description if you want to check it out. I definitely recommend it. So we import numpy, pandas, matplotlib.pyplot, also matplotlib.cm, and from scipy.io we'll import loadmat, and finally matplotlib inline to show our beautiful graphs. Now I will simply define the path to all my data sets. So data path 1 is going to be for x6 data 1.mat, and then we'll simply do the same data path 2 for x6 data 2.mat. Moving on to data path 3 for ex6 data 3. And I will define the path for the spam, train, and test as well. And we will use those data sets at the very end of the tutorial when we will build a classifier for spam using support vector machines. So train is done. Now data spam test is data slash spam train test, .mat. Perfect. Now we will need to write a function to plot our data. I decided to write a helper function here because we will be plotting quite often. So we will need x, y, x label, y label. We'll use pos label and neg label because this is mostly classification, right? And we'll also pass in x min max, y min, and y max. And set axis equal to none. So first we're going to set the parameters of the plot. We're actually going to set the figure size to make it nice and big for you guys so you can see it clearly on the screen. So I'm going to set it to 20 and 14. Now I will specify what will be considered as positive. So it's when the label is going to be equal to 1, and negative is of course when it will be equal to 0. Then if axis is equal to none, which by default it is, then we're going to set axis equal to plt.gca. Then we're going to draw a scatter plot, so axis.scatter. Pass in the positives. Then you pass in the y for the positives. I will specify the marker, so I want dots. So you can specify that by putting the letter O in strings. Then I will also specify a color. At this point, feel free to use any color you want. S equal to 50, and the line width will be equal to 2. And finally the label will be the pos label because those are the positive data points. Now I will draw another scatter plot, but for the negative samples. So it will be fairly similar to the line that we wrote above, only this time it's going to be for negative. So neg, column, comma, 0. And then again, so you pass in the y now, so x neg, colon, comma 1. The marker is still going to be a dot. This time we're going to specify another color so that we can differentiate them easily on the plot. So FFA 600, S will be equal to 50. The line width will also be equal to 2. And then you set the label equal to neg underscore label. Awesome. Now I will set the limits on the x-axis and then on the y-axis. So of course we'll just pass in the x-min and x-max, and then you do the same for the y-axis, so y-lim, and then you pass in the array from y-min to y-max. Now let's set the label for x. So set x label will be x label simply, and we'll specify the font size. I'm going to put it to 12, and you do the same thing for y label. So you set y label, pass in y label, and specify the font size as 12 as well. Then we will specify the position for the legend. So axis.legend is a box. Sorry, is a B box. To anchor equal to 1, 1, and fancy box will put equal to true. So let's start the coding portion by exploring the effect of regularization on SVM. And we'll start off this time with a small regularization parameter. So first, let's see what our dataset looks like. So data 1 is load mat, the data path number 1. X will be data X, and the Y will simply be data Y. And now we will plot the data set. So we use our function plot data, pass in X, pass in Y. The label will be X and Y. Then the positive label will simply call it positive. The negative will call it negative. We want the plot to be from 0 to 4.2 and then from 0 to 5. And I made a mistake because it should be data 1, not data. All right, and you see this following plot. So as you can see, the positive is in dark blue, the negative is in yellow, and you see that this data set is clearly linearly separable, and you also notice this outlier on the left. So now let's see with a small regularization parameter what will happen to that outlier, if it will be classified correctly or not. So we start off by importing SVM from sklearn, and we'll set the regularization parameter to 1 for now. So CLF will be equal to svm.svc. The kernel will be linear because, as you can see, we can use a straight line to separate the classes. C will be equal to 1, and then you specify the decision function shape to OVR. Then you fit the model on your data. And now we will plot the data as well as the boundary. So here actually we can just grab this line from the previous cell because it will be exactly the same. We're just plotting the same data again, and now we will plot the boundary on top of this data. Sorry, I accidentally ran this cell. But now let's actually plot the boundary or the hyperplane. So we start off by specifying x1 and x2 to be a numpy.meshGrid, and then we pass in np arrange. So we want from 0 to 5, and from with steps of 0.01, and np arrange. Oh, sorry, this should not be here. This should be inside the big bracket of meshGrid. So np arrange from 0 to 5 as well, with steps of 0.01. So I'm taking small steps here to make sure that we plot a smooth hyperplane, as smooth as possible. Then Z will be the prediction. Pass in np.c underscore x underscore 1.ravel, and do the same with x2.ravel. Then Z is going to be equal to z.reshape x1.shape. And now we are ready to plot the hyperplane. So plt.contour, you pass in x underscore 1, x underscore 2, pass in z, pass in 0, 5, and the colors will be black, so B. And there is a mistake. We have a warning here. No contour levels were found within the data range, and that is because okay, here's the mistake. It shouldn't be a comma, it should be a point, so 0.5. Perfect. And you see this plot here with our hyperplane, which is a straight line in blue, and we have and you can see here that the outlier was not taken into account and is in this case misclassified. So now let's see what happens if the parameter is very high. So feel free to pause the video and try it on your own as an exercise, because the code will be very similar to the previous cell. So here we are going to use a large regularization parameter. We'll set it to C equal to 100. And actually I'm simply going to grab everything from this cell here and just copy paste it below, because the code is exactly the same. We are simply changing the value of the hyperparameter. So we don't need to import SVM again, and we'll simply use C equal to 100 and see what happens next. So as you can see now, the hyperplane shifted to account for the outlier. But in this case, we are likely overfitting, which means that the model would not generalize well. So ideally, we will go with the previous model that we built. So now let's try an example with a non-linear boundary. So SVM with non-linear boundary. So for that, we'll need our second data set. So data 2 is load mat data path underscore 2. And like before, we'll specify the x and y and plot our data set. So x2 will be data 2 x, y2 will be data 2 y. And now we will use our helper function to plot the data. So pass in x2 and y2. Again, the label will be simply x and y. For the class labels, we'll simply use positive and negative. And now we will set the limits on the x-axis, so 0 to 1, and on the y-axis, it's going to go from 0.38 to 1. And there you go. So as you can see now, clearly a non-linear boundary, but the classes seem to be separable. So let's see how SVM will be able to do that. For this example, we will use a radial basis function for the kernel. Here we must define gamma, which is a parameter that specifies how far the influence of a data point reaches. A low value means very far, and a high value means close. And you can express gamma in function of sigma. So let's define sigma as being equal to 0.1. And then gamma will simply be 1 over 2 sigma squared. So 1 over, open brackets, 2 times sigma star star squared. Perfect. Then our classifier will be equal to svm.svc. We pass in the kernel, and this time is going to be equal to RBF. So for radial basis function, gamma will be equal to gamma. We set the regularization parameter to 1, and the decision function shape will again be equal to OVR. Next, we fit the classifier to our data. So x underscore 2 and y underscore 2 dot revel. Then we will plot the data set. So again, just grab this line from the previous cell and paste it under, because we are simply plotting the same scatter plot as before. And now we will plot the hyperplane, so the actual boundary from the SVM algorithm. So again, as before, x underscore 1, x underscore 2 will be a mesh grid, You range from 0 to 1 with steps of 0.03. So here the steps are going to be slightly smaller because we are drawing a non-linear boundary, and again, it's just to make it as smooth as possible. And from 0.38 to 1 for y. Then z will be equal to the prediction. Pass in np.c underscore. This is actually just to stack the predictions, by the way. So x underscore 1 dot ravel, x underscore 2 dot ravel. Then we will reshape z. So z dot reshape will take the shape of x1. So x underscore 1 dot shape. And now we are ready to plot the hyperplane. So plt dot contour, pass in x1, pass in x2, 0.5, and then colors will be equal to blue. And now there is a big mistake. Input z must be 2D. And easy enough, I forgot to pass in z. So x1, x2, z, and then the array 0.5, colors equal to blue. And there you have it. We can see in blue the boundary that SVM predicted for us. And you see it's doing a pretty decent job at separating everything. You see you have a few points misclassified here and there, but otherwise a good nonlinear boundary. But now let's explore a situation where the data is not easily separable. So for that, we'll explore the third data set. So load mat, data path underscore 3. As before, x underscore 3 will be equal to data 3x. Y underscore 3 will be equal to data 3y. And now we will plot the data using our helper function. So plot data, we pass in x3, y3. The labels will be the same, so x and y. Positive and negative for the labels. And we want to plot from minus 0.55 to 0.35 and from minus 0.8 to 0.6. So that makes the data points nice and centered. And as you can see now, there is a clear overlap between both classes. And so there is no clear boundary between each class. So this is when we need to use cross-validation in order to find the best parameters for the best boundary. So I will specify a list of possible values for sigma. So we'll go from 0.01, 0.03, 0.1, 0.3, 1, 3, 10, and 30. And we'll do the same for the regularization parameter c. So the same values, 0.01, 0.03, 0.1, 0.3. And then 1, 3, 10, and 30. Perfect. Now I will initialize an empty list of errors and an empty list for sigma and c. So for each value in sigma, and then for each value for c, we will define a classifier and we will fit it. So CLF is going to be equal to svm.svc. The kernel will be RBF again because the boundary is likely nonlinear. Gamma will be equal to 1 over 2 times each squared. And then after 2 brackets, we pass in the value for c, which is going to be each underscore c. And the decision function shape will be equal to OVR. Perfect. Then we will fit it to our data. So x underscore 3, y underscore 3, dot ravel. And we will append the errors to our list we defined earlier. So we're going to spend clf.score on data 3 x val and data 3 y val dot ravel. And then we're going to append to sigma c the value for sigma and for c as a tuple. Now running this, I have a mistake. That's because simga should actually be sigma, and I still wrote simga at the very end. Yeah, right here, simga c is actually sigma c. Perfect. So the loop ran, it is finished. So now we can see what value for c and for sigma is the best. So index will be np.argmax, pass in errors. Sigma max and c max will be equal to sigma underscore c at that index. And now we can print out the values. So the optimal value of sigma is colon squiggly brackets sigma underscore max, and we'll print the optimal value for c as well. And as you can see, we get an optimal value of 0.1 for sigma and 1 for c. So now we can fit an SVM algorithm. So we set sigma equal to 0.1, gamma is going to be equal to 1 over 2 times sigma squared. Then we will pass in those parameters to our classifier. So the optimal classifier is svn.svc. The kernel will be RBF. Gamma is equal to gamma, c is equal to 1, and the decision function shape is OVR. Now we will fit our classifier to our data. So x underscore 3, y underscore 3 dot ravel. Then we will plot the data. So again, just go back up. Let's grab this line here and paste it back in our current cell. And as before, we will now find the points for the boundary and we will plot it. So x1 and x2 is np.meshGrid. Pass in np range from -0.6 to 0.4. And we'll take steps of 0.004 to make it smooth, and np range from -0.8 to 0.6 in steps of 0.004. Z is then going to be the optimal clf.predict, and we will stack the predictions. So np.c underscore. We pass in x underscore 1 dot ravel and x underscore 2 dot ravel. Reshape z dot reshape is x underscore 1 dot shape. And now we will plot the boundary. So plt on contour, pass in x1, pass in x2. Pass in z, 0.5 in brackets, and the color will be blue. And the mistake again here is I wrote simga instead of sigma. Very sorry about that, guys. Hopefully you're not making the same mistakes as I am. And as you can see here, we have our best boundary found from cross-validation with support vector machine. So it's actually not that bad. And finally, let's use SVM for spam classification for our emails, right? So spam train, we're simply going to load the data set called data path, and I called it spam train. Then spam test will be equal to load mat, and you pass in data spam test. We will set the regularization parameter to 0.1, and then X train will be spam train, and we pass in X. Y train will be spam train, and we want the column Y. Then X test will be spam test, pass in X. Y test will be spam test, pass in Y. Our classifier, so CLF underscore spam, will be again svm.svc. We will start with a linear kernel, see how that performs. So kernel is going to be linear. The C parameter will be equal to C. We set it above. And the decision function shape will be equal to OVR. Then we fit our classifier to the train set. So we pass in X train and Y train ravel. And then we will calculate the accuracy. So CLF underscore spam dot score. And we will score against spam train X and spam train Y dot ravel. And then we will test for the test accuracy. So again, CLF underscore spam dot score, and you pass in X test and Y test dot ravel. Finally, we will print out those scores. So the training accuracy, squiggly brackets, pass in train underscore ACC times 100. So we have it as a percentage already. And we do the same for the test accuracy. Running everything, we have a key error for X. Yes, that's because here it should be X test and Y test. Sorry about this little mistake. So if we run this cell now, our model is training and fitting, and you get a training accuracy of 99.8% and a test accuracy of 98.9%, which is very good. So that's it for SVM. We covered a lot in this video. If you learned something new, please give a like to this video and also subscribe to the channel, as I have more content coming up about machine learning, but also deep learning, and we'll move on to more advanced concepts. Stay tuned.